Alright, hi Year 12, this is Mr. Lim here again, and this is our third pH calculations video, so that's going to be fun. Alright, we're going to learn to do some calculations, yeah. Alright, so we have heard from the last video that the self-ionization of water has a K value, and that K value is actually 1 times 10 to the negative 14 at 25 degrees Celsius, okay? So if you don't see a temperature associated with a pH calc or a calculation associated with this K value, then you're going to assume that it's at 25 degrees Celsius, right? And that value is 1 times 10 to the negative 14, right? The value is called Kw. All right, since the only two substances in this equilibrium system are the hydronium and the hydroxide ions, the product, which means that you multiply them together, of the two concentrations must be equal to Kw, okay? So, well, that whole idea of in the last video about when you increase the concentration of the hydronium ions, you have to decrease the concentration of the hydroxide ions, and they are linked to each other. The idea is that when you multiply those two things together, they must equal 1 times 10 to the negative 14. So you can use that to work out the concentration of each of the ions using the concentration of the other. All right, so let's go through some examples. Let's do these ones here. So calculate the concentration of hydroxide ions in a 500 ml solution with 12 grams of hydrogen chloride gas dissolved into it, okay? So this is actually just a basic, this is working out the hydroxide ions from the hydrogen chloride gas. So let's go walk through this one, so let's do it. So we will first of all work out the number of moles of HCl, right? Which would be 12 over 1.008 plus 35.45. which would be equal to 0.329 moles. Okay, so that's the number of moles in that HCl that is about to be dissolved into that solution, right? Then you can work out the concentration of that HCl, which will be equal to the 0.329 over 0.5, which happens to be 0.658 mole and mole per liter. And if you know that HCl is a strong acid, you can therefore say that the concentration of hydronium ions is equal to the concentration of HCl, which means that it is 0.658 mole per liter again. Okay, now this step here is quite important, this last step that we've just done, this one here, because you've got to show that you understand the link between the substance and the hydronium ions. You've got to do everything in hydronium and hydroxide ions for this calculation. So then you do the last bit, which it looks like we'll have to move over here a bit. All right, so the concentration then of the hydroxide ions, right, is equal to 1 times 10 to the negative 14, which is the Kw value, over the concentration of the hydronium ions. Okay, why is that? Let's go have a look at this particular thing. Maybe I'll just do it over here. Right, so if we have Kw is equal to the concentration of H3O plus times the concentration of OH minus. Okay, so if we have 1 times 10 to the negative 14 here, right, and then it's, we can rearrange the equation, right, so that the OH minus, okay, we have to bring the H3O plus to the other side, so it would be Kw over H3O plus, okay, alternatively, H3O plus is equal to Kw over OH minus concentration. Okay, so that's the idea about rearranging that equation. So now we come back to this. Okay, so if we have the concentration of OH minus is equal to that over that, which happens to be then 1.519 times 10 to the negative 14. Okay, so that's that one there. Okay, let's try something else. Okay, so calculate the concentration of hydronium ions in an 800 ml solution with 12 grams of sodium hydroxide dissolved in it. Okay, so similar process. Maybe we'll just use a smaller pen and we'll just go zoom in a bit more so we can more space. So the number of moles of NaOH will be equal to, again, 12 grams over 22.99 plus 16 plus 1.008, which will be equal to 0.3 moles. The concentration of that NaOH, okay, it's in 800 mils, so it'll be 0.3 over 0.8, which happens to be 0.375 moles per liter. So then we have to always transfer this into the concentration of hydroxide or hydronium ions from the concentration of whatever else we've got. Okay, which happens to be 0.375 again. And then finally, we can work out the concentration of hydronium ions from this. So the concentration of hydronium ions will be equal to 1 times 10 to the negative 14 over 0.375, which happens to be 2.667 times 10 to the negative 14. Okay, and that makes sense because it's a small value because you've added a whole bunch of sodium hydroxide to that thing. And then you could use that to work out the pH. You just do negative log of that value. Okay, then let's have a look at this last question. Now this last question, calculate the pH of a mixture of 12 mils of 0.4 mole per liter sodium hydroxide and 24 mils of 0.3 mole per liter barium hydroxide. I've rewritten this question over here. I might just grab that and move it a little bit more this way. Then we don't have that one, so we'll just do this one over here. Okay, so let's go do this one here. So we need the pH of this mixture. So we've got some sodium hydroxide and some barium hydroxide. And so when you do these calculations, you've got to really make sure that you're writing out everything in the annotation. So we're working out the number of moles of NaOH first. Okay, so it's CV, so it's 0.4 times 0.012, which happens to be 4.8 times 10 to the negative 3 mole. We'll save that as A. Then we'll do the number of moles of barium hydroxide. And hopefully remember that barium is 2 plus, hydroxide is a 1 minus, so therefore it's a Ba bracket OH bracket 2. Okay, so this is 0.3, because it's 0.3 moles per liter, and timesing it by 20.024, which happens to be 7.2 times 10 to the negative 3 moles again, and that's B. Okay, so from this, we have to say that, okay, they're both bases. We're going to add the bases together, add the hydroxides together. So we have to work out how much of these hydroxides are from the NaOH. Well, that's just going to be A, because it's going to be a 1-to-1 ratio from the NaOH and the OH minus. Okay, how many moles of OH are we going to get from the barium hydroxide? Well, that's going to go be B times 2. Which happens to be 0.0144, which we'll call C. Okay, so then we can work out the number of moles of OH total, which will be equal to A, which is from the sodium hydroxide, plus C, which is from the barium hydroxide, which happens to be 0.0192 mole. Okay, now because we need to work out this in pH, and we have to get the to the concentration of hydronium ions, we need to do everything in concentration. So let's do this in concentration. Oops. Concentration of OH minus is equal to the 0.0192 over the total volume, which is 0.036, which happens to be 0.533 mole per liter. Okay. Now I've got the concentration of hydroxide ions, I can work out the concentration of hydronium ions because I want it to get the pH. 1 times 10 to the negative 14, I'm using the KW equation, over 0.533, which happens to be 1.875 times 10 to the negative 14 mole per liter. Very small value. And therefore, I can work out the pH as negative log and that value, which happens to be 13.73. No unit on pH. All right, so That's how you can use that when you're adding two bases together. Okay, so let's have a look at what's next. Okay, the pH equation can be used to determine both the hydronium ion concentration and the hydroxide ion concentration, right? So we just did that. I think we did that. So like you use pH to work out the hydroxide concentration. So let's have a look at this next question. Calculate the mass of sodium hydroxide needed to change the pH of a 300 milliliter solution from 8.6 to 11.4. So let's move this a bit bigger. There we go. All right, so let's go through that idea. So we've got a pH, we got a 300 liter solution. It's initially at pH 8.6, which is basic, and we want it to go to 11.4, which is even more basic, so we need to add some sodium hydroxide. So first of all, we would need to work out how much hydroxide ions are already present, because remember, it's at 8.6, it's already got hydroxide ions present. So let's work out how many hydroxide ions are present when it's at pH 8.6. So let's do this. We can work out the concentration of H3O plus, right, from the pH. So we would say that it's 10 to the power of negative 8.6, and that's the concentration of H3O plus, which happens to be 2.512 times 10 to the negative 9 mole per liter, right? Then we can work out the concentration of OH minus using Kw, so 1 times 10 to the negative 14 over that value, which happens to be 3.981 times 10 to the negative 6 mole per liter. And then we can work out the number of moles of OH minus, and this is all at 8.6. So you need to annotate your information. So this is the number of moles of OH minus at 8.6, which will be 3.981 times 10 to the negative 6 times 300. Okay, which happens to be 1.194 times 10 to the negative 3 moles. And I'll save that as A, that's my initial value. Okay, now that's actually quite a small number, and that makes sense because 8.6 is quite close to 7, and there are very, very small concentrations. So it's a relatively small amount of moles of hydroxide ions to begin with. Now, at pH 11.4, there'll be a different number of moles, and we need to work out what that number of moles is. So again, we would do the same process, except I want the concentration of H3O plus now at 11.4. So this is the final concentration. Okay, so that's 10 to the power of negative 11.4, which happens to be, where is it? Here, 3.981 times 10 to the negative 12, which is a small amount, that makes sense, right? Mole per liter. I can work out the concentration of OH minus at 11.4, which will be equal to 1 times 10 to the negative 14 over that number, which happens to be 2.512 times 10 to the negative 3 moles per liter. That's the concentration of OH minus at 11.4, and then I can work out the number of moles of OH minus at 11.4. Okay, what's that going to be? It's going to be 2.512 times 10 to the negative 3 times 300, which happens to be 0.754. Okay, moles, that's B, and that's effectively the final concentration of OH minus. So we know how much there needs to be at the end. We know how much there was at the beginning. We can work out how much we need to add to it. So for number of moles of OH minus, we need to add to it will be equal to the number of moles of OH minus at 11.4, subtract the number of moles of OH minus at 8.6. Okay, it's effectively how much we need at the end, take away how much we started with. And that's how much we need to add. So it's going to be B take away A, which happens to be 0.752 moles. And you'll notice that these two values aren't very different, because that makes sense, because this value is very, very small. Okay, you only started with a little bit, right? And so you're going to need to add effectively all of the extra has to be added to it. All right. How do we get that 0.752 moles? Right, well, we need to add in some sodium hydroxide. So we need the number of moles of sodium hydroxide needed will be equal to the number of moles of OH minus needed, or added. And so therefore, we need, that value, 0.752 moles. And then the mass of NaOH needed will be equal to 0.752 times 39.998, which is the molar mass of sodium hydroxide, and you get 30.09 grams. Okay, so that's how you would answer that particular question. Okay, if you need to say how much do I need to add to get it to a certain pH. Okay, this question becomes a lot more tricky when you start from an acidic point. If you do start from an acidic point, you have to work out how much you need to neutralize all the acid that's present, and then effectively that gets you to 0, and then how much you would need to still add to bring it to the concentration that you need it to be at. All right, so that would be extra tricky. I'm sure there'll be a practice question in the booklet. Let's move on. Right. So, if a pure water sample has equal amounts of hydronium and hydroxide ions, then we can use this knowledge to determine the pH of a sample if we're given the Kw at a different temperature, or even if we're given Kw at 1 times 10 to the negative 14. Okay, if Kw is 1 times 10 to the negative 14, this idea still works. But let's have a go through this. So, the idea is that if Kw is equal to 1.995 times 10 to the negative 13. Therefore, 1.995 times 10 to the negative 13 is equal to the concentration of H3O plus times OH minus. Now, remembering, if the H3O plus concentration is equal to the concentration of OH minus, since they're going to be the same, you can say that they, are the exact same thing. So 1.995 times 10 to the negative 13 is equal to concentration of H3O plus squared, because you're going to multiply it by itself. Or you can just write x squared. Okay, so x being the concentration of either the H3O plus or the OH minus. All right, so if it's that value squared, then the H3O plus will be equal to the square root of 1.995 times 10 to the negative 13. Okay, which will happen to be 4.47 times 10 to the negative 7. And then if you do the pH calculation on that, pH is equal to neg log 4.47 times 10 to the negative 7. You get, some value, 6.35. Okay, all right. If Kw is equal to 1 times 10 to the negative 14, okay, if you do this same thing equation, you do concentration of H3O plus is equal to the square root of 1 times 10 to the negative 14. That happens to be equal to 1 times 10 to the negative 7. And if you work out that pH, that is pH 7. All right, so pH 7 means that it'll be 1 times 10 to the negative 7 moles per liter of H3O plus, and they'll be equal at 25 degrees Celsius. And that's why that's pH 7 is neutral, right? That's the reason why that is there. Okay, a couple more calculations, all right? So this one here, limiting reagent again. So limiting reagent, but this time is going to be in excess. The sodium hydroxide or the base is going to be in excess. So let's go through this calculation, and then I'll go have another calculation for you to try, and you can go do that on your own. Let's do this one, okay? So if a 120 mole of 0.4 mole per liter diprotic acid is added to some sodium hydroxide, determine the final pH. So this has the idea of, okay, well, I have some acid, I have some base, they're going to neutralize, and whichever is going to be in excess is going to determine the pH of the solution. So let's get started. So first of all, we'll work with the acid. the number of moles of, and we're going to call it H2X because this is a diprotic acid, okay, H2, and it's going to be 0.4 times 0.12, because that's its number of moles, which will be equal to 0.048 moles, okay? This is the number of moles that I have. Then I can work out the number of moles of NaOH that I have, which will be equal to 0.9 times 0.2, which happens to be 0.18 moles. So if I know that, this is a diprotic acid, I know that it's going to react with 2 of the NaOHs because it's going to react twice with it, right, to form Na2X plus 2H2O. So this is the equation. You should always write out the equation, right? And so therefore, I'm going to work out which one's the limiting reagent. So I pick one of the two reactants. I'm going to pick the number of moles of NaOH needed, right? And this one's going to be the number of moles of H2X times 2, okay? Which happens to be 0.096 moles. Now I'm saving all these numbers in the calculator, so you should be saving them as well. Just remember that saved numbers are always better than just copying the value, otherwise you're going to have rounding errors later on in the calculation. Right, so since the number of moles of NaOH needed is less than the number of moles of NaOH have, therefore the H2X is the limiting reagent. We should have kind of knew that already. All right, so let's continue on. All right, so the number of moles of NaOH excess then will be equal to the number of moles of NaOH that you started with, have, subtract the number of moles of NaOH, which was effectively needed or consumed or neutralized, whatever you want to use, right, which will be equal to the 0.18 subtract the the 0.096, which happens to be 0.084 moles. Right, so that's the amount of moles that I have excess. I can work out its concentration of NaOH excess, which will be equal to 0.084 over 0.32. Where's this 32 come from? It's the 320 mils that you've got combined, okay, which happens to be 0.2625 mole per liter. Okay, once you've got that concentration, you have to convert it into hydroxide ions. Then you can work out the concentration of hydronium ions, 1 times 10 to the negative 14 over the 0.2625, which happens to be 3.8, 1 times 10 to the negative 14. And then you can do the pH is equal to the neg log of that value, which happens to be 13.42. Okay, all right. And then here's the last question. You should try it yourself before the answer magically appears. And ta-da, here it is. Okay, so just be aware that this annotation is in the solution. This is the amount that you added. This is the amount that is neutralized by the solution. This is excess is equal to the added, take away the neutralized, and therefore after that you can work out its pH. All right, so calculations, they are fun, all right, but they're a good way to get lots of marks. All right, adios.